Okay, if I could have your attention up here, this will actually go by kind of quickly, and if we have a time, I'm hoping that we get to have people come up to the camera today. So if I do my lesson kind of quickly, I can have people come up to the camera, and then you'll be the teacher for about 5 minutes apiece, or 3 minutes apiece, something like that. All right, so let's, what I'm going to do is, remember how we did I said there were 3 parts to the chapter, and so let's talk about scientists just briefly. And I always ask questions on the test about the experiment. So this guy here named Rutherford, kind of an interesting experiment, but it really changed the whole idea of what an atom was. And let's see if we get the picture here. What is this box made out of? Not gold. Lead. Lead is very, very dense. And what's inside there that could hurt you? Some kind of a radioactive material, right? Now, I'm not going to get into that very much, but a radioactive material, you know the actual nucleus of those atoms, some of them right now, some of them 10 minutes from now, they actually break apart. And so in this case, this radioactive thing sends off a thing called an alpha particle. Now, an alpha particle is 2 protons and 2 neutrons. Can you look up here, and say how much you know about this? Uranium has 92 protons, doesn't it? That's why it's number 92. What would happen if uranium threw away, the nucleus got rid of 2 of its protons? Would it still be uranium? No. And that's what radioactive materials do. They throw away part of the nucleus, and actually many of them change into another element. Also, but what happened is these little bullets that are being fired are 2 protons and 2 neutrons. So what charge would these little bullets have? What do you think? 2 plus and nothing. That's plus, isn't it? So they got little positive bullets, and he's firing at this screen. Now this screen is coated with a chemical that when the bullets hit it, you can't see the little bullets come out. They're incredibly small. They're even smaller than it's like the nucleus of a helium atom. Anyway, when they hit this screen, it makes the chemical sparkle. The word is scintillate. And it makes it sparkle. See that? And then that stops sparkling. But anyway, then he takes this really thin piece of gold and he puts it right in front of the beam. And so what happened back here? Any sparkling? What do you think? Any sparkling? The beam, he put a piece of gold right in front of it. What do you think? And he had almost exactly the same number of sparkles as he did before. It's like almost every one of those little bullets came straight through that piece of gold. He said, wow, I don't understand that. But not all of them. He came around the side and looked to the side, and he saw maybe 1 or 2 here, 1 here, 1 come back here. Every once in a while, you'd see one that would come back, would be deflected. So here's what he said. I can't believe that the atom is like the plum pudding, because the plum pudding is big and all the positive stuff's everywhere. I should have hit lots. My little positive bullets should have been deflected all over the place by that. But why? He said, why did they go straight through? He said the atom must be mostly what? If we had a model of the atom, remember I talked about a baseball stadium? You put a little P at second base, and the first electron is past the home run fence. If I had that model sitting on its end, you'd say most of the atom is empty space. Most of the atom is nothingness. Now that doesn't make sense to you, but that's what he said. He said most of the atom is nothingness, but there's an incredibly small nucleus, and that's where 99.99% of the mass is, and it has to be positively charged, because my positive bullets, when it got close to a nucleus, it would have been repelled, didn't it? Like charges repel. What about unlike charges? What's plus and minus do? They attract, don't they? What's plus and plus do? They repel, right? What about minus and minus? They repel. Do you understand that experiment? That's the first time, and in every book today, we still think the atom is mostly empty space with an incredibly small nucleus. And then the last person they mentioned in the book is way on this page here. This person actually worked with Rutherford, but it was later later, I forget how many years, 15 years later maybe, there was some problem with the nucleus. He said, that nucleus seems to have more mass than just protons. And so then he was given credit. His name was James Chadwick, and he was given credit for discovering the neutron. So that's the whole story of the history part of the chapter. Everybody got that? The history part of the chapter is done. All right, let's go back to this one now. And I'm going to go as fast as I can. This will be the third time I've done the world of mass. Then we'll get into the world of charge. All right, in the world of mass, that is the world of the nucleus. It's the world of isotopes. It's the world of protons and neutrons. So if protons have a mass of 1 AMU and neutrons have a mass of 1 AMU, look at my model here. When I look at that model, I see there are 3 protons in the nucleus. For sure, if you have 3 protons, what atomic number do you have to have? If you have 3 protons, what's your atomic number? 3. And what element do you have to be? Lithium. You got that? That's like a fingerprint. Now, let's look at the rest of the nucleus. 3 protons and 4 neutrons. What's the total mass of the nucleus? 7 what? Not grams. Atomic. What do you call? Did somebody say AMUs? Atomic mass units. All right. So anyway, what we do then is we put the symbol lithium, and this is the atomic number 3. And what's this up here? The mass number. So the mass number goes up here. The atomic number goes here. What's interesting is this is the number of protons and neutrons. This is the number of protons. So what is the mass number minus the atomic number? That'd be a great test question. What's the mass number minus the atomic number? Number of neutrons. Thomas, you with me? What are you holding your hand? Huh? Where's your packet? Okay. All right, then we turn the page. And we have 3 different atoms, don't we? They look different, don't they? But there's something about them that's alike, isn't it? They all have the same atomic number, and therefore they have the same symbol, capital H, capital H, capital H. They're all hydrogen. Which one of these is hydrogen? All of them. Which one can you make water out of? All of them. Which one's radioactive? Let's see if you remember that. Only one of them is this one. And by the way, this is the only isotopes that have actual names. The rest of them have really boring names like carbon-14, U-235. See that? That's their name. But this is protium. That's the first, proto the first. Deuterium, I have a mass of 2. Tritium has a mass of 3. They actually use tritium, I don't want to get too much into this, but to make nuclear warheads. To make nuclear warheads, they use a form of hydrogen that is radioactive, and so we have to find tritium. Now, out of 1 million hydrogen atoms, maybe only 2 or 3 out of 1 million are tritium. And so we have to isolate it and get rid of the other isotopes and get those to find tritium. So if we don't make tritium, if we don't find tritium, and we got a lot of water on the planet, don't we? So there's a lot of hydrogen on the planet. We can find it. It just takes a lot of money to get it. Let me give you a 60-second story about the world, okay? Do you know where, you know Iran? You know Iran? You heard Iraq? Iran? Okay. Okay, so Iran, and this is my opinion, it's a little bit editorial. Iran, I think, pretty certain, they've said this out loud, they would like to wipe at least one country off the face of the planet. Does anybody know what country that is?
Iraq.
Well, not Iraq. They'd like to take that over.
Russia.
What is it?
America. Iraq.
No, well, maybe America. America would be number 2, but who would they want to wipe off before America?
Sweden.
Israel.
Israel.
And they've actually said that they would like to wipe them off the map. Now, they also said we would like to be able to have nuclear power plants to make electricity. Like we have them, don't we? And yet they have probably 500 years of oil sitting underneath their country. They don't have to make nuclear power plants, but they said they want to. Well, you know, to make a nuclear power plant, you have to have a certain kind of isotope of uranium called U-235. But if I give you a rock of uranium in it, it has a lot of isotopes in it. It costs a lot of money to separate the isotopes. So if you watch the news, you'll hear about this thing called a centrifuge. Have you heard that? Okay, so a centrifuge is something that spins around really fast. Okay, got that? Is everybody with me? This story is really actually worth it. It's worth your time. What they do is you take uranium and you vaporize it. You change it into a gas. Now, all the isotopes of uranium are in there as a gas, and then you spin them in a centrifuge. Now, you know what happens in a centrifuge? If you're the real heavy isotope, like 238, you go toward the outside. What if you're a U-230? You stay in the middle. What about U-235? Kind of right there, see that? So what they do, the centrifuge is meant to separate the isotopes, and so if you want to go after and just go get the U-235, and by the way, yes, you can make that for power plants, but what else can you make with U-235? Oh, you guys know anything about the news? Maybe it's all right. That's okay. Then maybe I shouldn't tell you so you can sleep better at night. But you know what they want to do? They want to build, I think they want to build bombs, nuclear warheads. And I think they would love to tell the world that they're getting U-235 to use it with their power plants, but I feel certain they're going to make nuclear warheads out of it. Yes? Okay. So anyway, what happened is, real quick story, about 10 years ago, they were spinning their centrifuges, which they said they weren't allowed to do. They had some kind of treaty or something, but they're doing it anyway. And then what happened was, all of a sudden, all their centrifuges broke. And somebody put some spyware, or not spyware, some malware on got inside their computer somehow, their system. And it told the centrifuge to spin at 3 times their normal rate, and it broke them. And I wonder who did that. But anyway, it's interesting. It's funny that that's a different kind of a warfare where you want to make U-235, I'm going to break your centrifuges. Now it'll take you at least a couple of years for you to get back into that. So I don't know if it was the United States or Israel or both of them, but that's what happened. Okay. Well, everybody okay on the world of mass, anything? So the world of mass, if you tell me what words go along with the world of mass, I'm listening. The world of mass is the world of what? This will tell me whether or not you're paying attention. The world of the nucleus. Protons and neutrons. What other words go with the world of nucleus? I mean the world of mass. Isotopes. Nucleons. Mass number. Remember mass number? Okay, so if you'll remember that, then you will not confuse the word isotope with the new word I'm going to use today called ions. Okay? All right, here we go. Let's crawl over that brick wall, and I don't want you to think about the world of mass right now, okay? We're crawling over the wall, and we're going to get into the world of charge. So what they did is they started looking at the atom, and they started looking at it not in a mass sense, but in an electrical charge sense. And they found out that the proton, and I know it has mass, but we're not talking about the mass. The proton had a charge, and I had the number written down here, but the number was, I don't have it here. It's like, let me see what I have written down here. 1.67 times 10 to the minus 19th coulombs. That's how much charge it had. Well, I can write that number down for you, couldn't I? I could even tell you to memorize it, but I'm not going to do that. Because guess what scientists said? I hereby declare that little tiny number of coulombs, I'm going to call it 1. A charge of 1. That's 1 bundle of charge. Isn't that pretty smart? And then, what about the electron? What charge did it have? Did it have the same number of coulombs? So I don't know. It did. Oh, it did. And so we called that 1. And then somebody made a definition, said, well, if this charge does such and such, I'm going to call you plus. And if you didn't, I'm going to call you minus. And that's where we got that. So in middle school, when they told you that protons have a +1 charge and electrons have a -1 charge, that's how that happened. Now, what was the charge on a neutron? What was the charge on a neutron? No charge, okay? I was in the store the other day, and I bought something. Right behind me, somebody was buying something like, and it was a neutron. A neutron, he said, here, can I have this pack of gum? And then the neutron, so how much? It says, for you, no charge. Okay. Wait, no charge. But anyway, so the neutron has no charge. So in the world of mass, we don't talk about electrons. In the world of charge, we don't talk about neutrons. You get that? Yes? Okay. Well, here we go. So if we look at this model here, everybody see this model of an atom? How many pluses do you see? How many protons do you see? So I got 3 plus charges, and how many electrons do you see? Okay, that's 3 negatives, right? What does 3 plus and 3 minus have to be? 0. And we call an atom that has no charge, we call it an atom. It's called an atom. Some books will say neutral atom. Neutral atom, but if I say the word atom, you're to assume that it has no charge. When I look up here, these are all the atoms, aren't they? Unless I tell you, you're supposed to tell yourself they have no charge. So look up there right now. Look at sodium. How many protons does sodium have? Everybody in the room should know this. 11. Well, how many electrons does it have? Remember, I told you, unless I tell you, atoms have no charge. How can sodium have no charge when you told me it has 11 protons? How can he have no charge if he has 11 protons? Uh-oh, I'm losing you. What is it? That's right. Does that make sense? Let's look at uranium. Look at this guy here. Ready? How many protons does uranium have? Okay. How many electrons do you have? See that? See that? Unless I tell you, if I just say it's an atom, it's neutral, isn't it? Okay. So this guy is neutral. So what happens is, not in this corner, but this corner. This corner is where I let you know about the world of charge. Now, if this has 3 pluses and 3 minuses, then I want to write Li with nothing here. So writing nothing in that corner is actually telling you something. If I have 3 protons and I have no charge, then you know I have 3 electrons. Now, I hope I can teach this to you. There's something else I want to teach you. Most of the periodic table, and I don't know if you've ever seen this periodic table way over here. Ever seen that one? That's a pictorial. You can actually look at the pictures of every element that we know of. And I don't know if you can see that or not. See, it's kind of boring, aren't they? Hey, where's all the red stuff? And see, we only have about 100 and some of those boring elements. But God allowed them to combine into compounds and make everything. Everything you see here is mostly compounds. There's not very many pure elements in this room. You know that? Now, there are some mixtures. Anyway, what I want to show you is metals. See this little stair step here? Everybody see that? Okay, not counting hydrogen. Anybody who's below that stair step, all these, they are metals. Now, metals are neutral, but they, in a chemical reaction, they have a tendency to lose 1, 2, or 3 of their negative electrons. Now, what do you think would happen to lithium? I'll tell you right now that lithium has a tendency to get rid of one of its electrons. Now, I want you to think about this. What if you had, now lithium has 3 protons, and what if he only had 2 electrons, and this is where you have to fight your brain a little bit. He lost one of his negative electrons. What does he become? Positive. Metals have a tendency to become positive ions. And you say, what's an ion? An ion is a charged atom. If you're a neutral atom, you can't be an ion. So look right here in my hand. Protons, electrons. Ready? You're neutral. Protons more than electrons? Ion. Electrons more than protons? Ion. Get it? So what kind of ion would this be? I have to tell you, see, if I got rid of that electron right there, I would have to tell you that this guy was a lithium +1 ion. And this is where it gets kind of neat. And that's where I'm going to have you. Oops, there we go. All right, so let's go down here. And let's say, how much can this symbol here tell you? How much? Look at this right here and tell me all the information you know about looking at that. Sean, start me out, Sean. What do you know about? Tell me something you know about that symbol.
It's got a positive,
That what now?
positive charge.
And what is that called?
It's got
What do you call, starts with I? It's an ion, right? And so it's an ion. What kind of ion? Yes, so it's a +1 ion. And what else? Tell me something else you know. Luke, you want to tell me?
There's 11 neutrons and
11 what?
electrons and protons.
Okay, wait now, be careful. Go slower, go slower. Na tells me what?
That is sodium.
And that I'm sodium, right? And I also know that if you're sodium, what's your atomic number? Look in the periodic table. What's the atomic number?
11.
But 11, the atomic number is always the number of protons. So how many protons does sodium have? Everybody got that? What else can we tell? Somebody else, Matthew.
Has 13 electrons.
13 electrons? Okay, now, I'm going to give you a little clue, okay? You know why I had that little brick wall there? Because right now your mind is mixing the world of mass and charge. So let's go on one side of the wall or the other. What do you want to tell me about neutrons? If you want to talk about neutrons, we're in the world of mass, aren't we? What's the mass of this isotope? What's the mass number? What's the mass number of this isotope? And by the way, I know we have a whole week off, but if you don't get it now, all right, you got to get it now so that when I review it, you'll get it even better. Wait, yes, the mass number is 24. That's how many things are in the nucleus. So we know that you have 11 protons and 24 things in the nucleus. 11 of those are protons. So how many neutrons do we have? 13 what? Now, so we got, 11 protons, 13 neutrons, right? Is that correct? That's 24? Now let's do the world of charge. Tell me something about the world of charge. Thomas, you want to help me? And I'll give you a little hint. See a little +1? It's like a soccer game. The pluses are ahead by 1. There's more pluses than minuses. They're ahead by 1. So how many electrons do we have? The pluses are ahead by 1, and you have 11 pluses. So how many electrons do you have? Say it again. But the pluses are ahead by 1. The protons are ahead by 1. And you have 12. You have 11 protons, and the protons are ahead by 1. So how many electrons do you have? What if we play a soccer game, and I said, here's Caldwell, protons, and the other school's electrons, and I said, what's the score? Well, I forget the score, but I know we're up by 1. If we have 11 goals, and we're up by 1, how many goals does the other team have? But we're up by 1.
Oh, 10.
Okay, there you go. So by using this symbol, I can actually figure out that there are 10 electrons in this thing, isn't there? So what do you call something, an atom that has a charge to it? What's that called? What do you call an atom that has a charge to it? It starts with I. Ion. Yes.
Can I take my test in the back room?
No, you take it back there if you want.
Okay, that works.
Okay. All right. What now? It's right behind you. You know, in the middle.
Maybe it's
No? Middle? Middle? Hey, that's it.
Okay, thank you.
All right, here we go. Now I want to show you something here. Here, before this lithium was just by itself, when it was by itself, it had 3 protons and 3 electrons. So it was a neutral atom. It was an atom, wasn't it? And over here, chlorine was 17 protons and 17 electrons. It was just a regular old chlorine atom. But guess what? Metals have a tendency to lose 1 or 2 or 3 of their negative electrons. And guess what nonmetals tend to do, including hydrogen? What do nonmetals tend to do? Gain 1, 2, or 3 electrons. Now, if you're neutral and you gain extra negative electrons, what happens to you? Wait, metals were neutral and they lost some of their negative things, make them more positive, didn't it? What if you're a nonmetal and you tend to gain somebody else's negative electrons? What does that make you? Negative, isn't it? So take a look what happens. This is chemistry, ready? This is chemistry. You take a metal and bring it close to a nonmetal. And here's what happens. Lithium has a tendency to lose one of its electrons. So let's pretend it goes over here, okay? Now lithium has 3 protons and only 2 electrons, which gives it a +1 charge. So I have to write the symbol Li +1. Now we have a fancy name. There's a fancy name for a positive ion. And here it is. It's the word cation. C-A-T-I-O-N. Now what I like to do is write the T as a plus sign, and that reminds me that a cation is a what? A positive ion. Got that? You can always tell if somebody's ever had chemistry before. You ask them to pronounce that word. If they've never had chemistry, they'll say cation, like vacation. But if you've been in chemistry, they'll say cation. Get that? All right. Now, so here we have, now all of a sudden, the lithium has a plus charge on it. Got it? It's an ion. Now, what about the nonmetal, chlorine? He used to be 17 pluses, 17 electrons. Now he's 17 pluses, 18 negatives. So he must have a -1 charge, and I'd write this symbol like this. Everybody got that? Now, watch what happens. This is chemistry. Ready? What do you think happens when I put lithium and chlorine together? I lose an electron and become a cation, and there's a fancy name for a negative ion. Watch, a negative ion, anion. Okay? Now here is the first time you've seen this happen. What's going to happen? The plus ion cannot get away from the negative ion anymore. Why not? Why are they attracted to each other? Because they have opposite charges. Now, if you've never understood this, get ready. I'm going to tell you a sentence. Watch, ready? What kind of a bond do you think would hold ions that have different charges together? What kind of bond? And for the first time, you might understand why they use the word ionic bond. And what you're making is an ionic compound. What are ionic compounds made of? Starts with an I. Ions. What kind of bond holds them together? Ionic bond. And I'll tell you right now that the word that means you're an ionic compound, the word that means you're an ionic compound is that word right there. If you're an ionic compound, you're a salt. It just happens, and there are hundreds of salts. But what's the most common salt you have in your house? It's called table salt, and it's called sodium chloride. What's sodium? A metal. And what's chlorine? A non-metal. Oh, this is making sense now. Ready? Look down here at the bottom. You just made the compound called lithium chloride. Lithium chloride is what kind of a compound? What kind of compound? Starts with I. Ionic compound, held together by ionic bonds, and it's made up of ions that have opposite charges. And that's called a salt. What do you think? So maybe for the first time ever, you actually know what that is. Now, I don't have time to, I don't have time to have it come up on the camera, but when we get done, when we get back, I'll review the lessons and we'll play this thing called a grid game. So the grid game is where I call everybody up and they try to do one of these things, and we'll do that when you get back, okay?